Bismillahirrahmanirrahim. Welcome to the first part of 13th lecture of Statistics and Probability Theory. The topic of previous lecture was hypergeometric distribution. Hypergeometric distribution have four properties. The number one was experiment has two possible outcomes, success and failure. Number two was experiment is repeating a fixed number of times, and number three was each successive trial is dependent, and number four was probability of success does not remain constant. In binomial distribution, it was with replacement sampling case. The experiment was being happening on the basis of with replacement sampling, whereas in hypergeometric distribution, experiment is happening on the basis of the without replacement sampling. So this is the basic difference between the binomial and hypergeometric distribution. Topic of today's lecture is multivariate hypergeometric distribution. As you can see that hypergeometric distribution can be extended into multivariate hypergeometric distribution. This is same as we have extended binomial distribution into multinomial distribution. The hypergeometric distribution can be extended to treat the case where the capital N items can be partitioned into R cells A1, A2 up to so on till AR with A1 elements in the first cell, A2 elements in the second cell, and AR elements in the rth cell. We are now interested in the probability that a random sample of size n yields x1 elements from A1, x2 element from A2, and xr element from AR. It is obvious that in hypergeometric distribution we have only two possible outcomes, success and failure. So now, as the name of the distribution is multivariate hypergeometric distribution, so obviously it will have more than two possible outcomes. For example, the model of an urn with green and red marbles can be extended to the case where there are more than two colors of marbles. If there are ki marbles of color I in the urn and you can take n marbles at random without replacement. As you know, this is the extension of the hypergeometric distribution, so obviously this will also be the case of without replacement. Then the number of marbles of each color in the sample is K1. K1 is for the one color, K2 for the second color, up to so on, Kc for the category C or color C. It is representing the number up to which we can take or number of colors. So has the multivariate hypergeometric distribution. This has the same relationship to the multinomial distribution that the hypergeometric distribution has to the binomial distribution. The multinomial distribution is with replacement distribution, and the multivariate hypergeometric distribution is the without replacement distribution. Probability mass function of multivariate hypergeometric distribution. If n items can be partitioned into R cells as we have defined earlier, so the according to the scenario that we have divided into R cells A1, A2 up to AR, and each cell contains particular elements. A1 contains the small a1 elements, A2 contains capital A2 contains small a2 elements. So we have to associate random variables with each category. X1 is associated with A1, X2 is associated with A2, and the sample will be taken as small n. So according to the scenario, the probability mass function will depend on the random variables, as you know, and A1, A2, A are capital N and small n. As you know that in hypergeometric distribution, there are three parameters k, capital N and small n. Now, as we have more than two categories, so there will be A1, A2, AR instead of K here. So according to the scenario defined here, the probability mass function will be this: A1C X1, A2C X2, up to so on, ARC XR, and NC small n. So this is basically you are selecting X1 elements from A1, X2 elements from A2, and this is the uh, total number of outcomes, and these are the favorable outcomes. So if you sum up the number of elements selected, it should be equal to the sample size n, and the elements of all the categories, if you sum them all, it should be capital N, as capital N is the population. So just imagine if you have three categories, X1, X2 and X3. If you can see from here that you have colors, this is pink color, this is black color, and this is white color. So there are three categories. You can represent it with R1, R2 and R3. When you sum up them all, it should be equal to capital N, as they are capital N number of elements in this particular circle. So if you are taking the sample from this population of size small n, so X1 is associated with white color, X2 is associated with black color, and X3 is associated with pink color. And when you sum them all, answer should be small n, as this is the sample, and this sampling is done without replacement. As you know, this is the extension of the multivariate hypergeometric distribution, so sampling should be without replacement. So according to the scenario, if you have three random variables, so and you have three categories as well, random variable is associated with the category. So R1, C, X1, X1 elements are selecting from the R1 elements. These are the number of ways, how many ways you can select, or how many ways you can select R1 elements from X1. Similarly, according to the probability mass function defined for the categories before, for the R categories, now you have restricted it for the three categories. So this will be the probability mass function for three categories, R1, R2, R3, for multivariate hypergeometric distribution. And as you know, there should be the limit on the random variable. So x1 plus x2 plus x3 is equal to n, where xt is between 0 and n, and j is equal to 1, 2, 3, where j is representing the number of categories, as you have three categories. Example number 1. A group of 10 individuals is used for a biological case study. The group contains 3 people with type O, blood type O, 4 with blood type A, and 3 with blood type B. What is the probability that a random sample of 5 will contain 1 person with blood type O, 2 people with blood type A, and 2 people with blood type B? So you have to select the number of persons with specific blood types, and you have total 10 individuals, and you have categories of blood, that is O, A, and B, and O contains 3 people, A contains 4 people, and B contains 3 people. So as you can see from here that this is your sample space. Let us assume that this is our sample space and it contains 10 people, and it is divided into 3 categories, R1, R2, and R3. So this is for, let's say, for blood type O, blood type A, and blood type B, and O contains, uh, let me clear this. So this is blood type B. 3 people are of type O, 4 are of type A, and 3 are of type B. What you are doing, you are taking the sample of 5 persons. So what they are asking one should be of blood type O and 2 should be of blood type A and 2 should be of blood type B. Obviously, this is the case of the without replacement, as one person is selected and his or her blood type is tested. He or she should not be back into the sample. So this is or in the population. So this is simply the case of without replacement, and it is experiment is repeating a fixed number of times. This is n, and you are selecting 5 persons from it. So this is the experiment, number of trials are fixed, and you are selecting the person from this particular number of individuals, and you have categories of them according to the blood type O, blood type A, and blood type B. So according to the probability mass function, which is probability, if you remember, x1, x2, and x3, and this is A1, number of elements selecting from the category 1, A2, A3, capital N, and small n. So you want one person from the blood type O, two persons from the blood type A, and two persons from the blood type B, and X1 is associated with the first category or blood type O, X2 is associated with the second category, which is blood type A, X3 is associated with the third category, which is blood type B, and A1 represents the number of persons having blood type O, A2 represents number of persons having blood type A, and A3 number of persons having blood type B. So which will be equal to A1 C X1 A2 C X2 A3 C X3 whole divided by N C N. So on solving this, you will get 3 divided by 14, which is the probability of selecting uh, X1 is equal to 1, that is 1% of blood type O, 2% of blood type A, and 2% of blood type B.